Mr. Klein here, in a hat. It's no big thing. And I want you to take out your note packet and turn to this page right here. We're going to begin talking about limits. You know, a good way to talk about limits is to start by looking at a function like this. This is a rational function, or in other words, it's something divided by something. And my question for you is, what does the graph of this function look like? A good way to tell what the graph of the function looks like is to plug in some points. So when I plugged in 0, I got 1. When I plugged in 1, I got 2. And when I plugged in 2, I got 3. When I plugged in 4, I got 5. But when I plugged in 3, something weird happened. When I plugged 3 into this thing, I got 0 divided by 0. Uh-oh! It's an indeterminate form. Now let me show you why that happened. You could factor this numerator. Maybe some of you noticed that this factors to x plus 1, x minus 3. Well, that's important because if you look at the denominator, it's also x minus 3. Well, here's what that means, that you have an x minus 3 and an x minus 3 here. I know a lot of you are thinking, oh, I can just cancel those. Well, you can, except for there's one little catch here. For almost any value, in fact, for any value that's not 3, this and this don't matter because they're like a 1 and they go away. So if you plug in anything that's not 3, this function is equal to x plus 1. However, if you plug in x equals 3 to this, you get a 0 on the top and a 0 on the bottom, which gives us 0 over 0, which is undefined. Not sure if I've said so yet, but this symbol right here means undefined. Well, how do we show that off with a graph? We say, well, it's going to be this line, which is x plus 1, y-intercept of 1, slope of up 1 over 1, up 1 over 1. All right. Boom, 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 boom. Everywhere except for at 3. And at 3, we show off that undefined by drawing an open circle, or in other words, a removable discontinuity. That's what this is called. All right, so here's the big takeaway. Here's what I want you to know. We want to understand the difference between something called a value and something called a limit. A value is what actually happens at a point. So in the case of 3, the value would be what you get when you plug 3 into the function. And we know that the value in this case is undefined. There's no value there. It's an open dot. Contrast the value with the limit. The limit is what happens as we get really, really close to 3, but not actually at 3. So in other words, the limit is what are we approaching around 3. And in this case, you can see that we're getting really, really, really close to 4. So we would say the limit as x is approaching 3 of the function f of x is 4. It is important for you to know the difference between a value and a limit. So here's what the two words mean, value and limit. Again, value is what is happening at that point, and the limit is what's happening close to that point. So you would write those down. That would be great. Quick example. Let's put a number right here. Give me one of your favorite numbers. What's that? 4? You got it? Okay. So there's 4. Let's suppose this goes tick, 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 and I've got a graph, and that graph is going boop, 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 and then boop, 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 and then let's suppose that there's a dot that's out right here. If I asked you what is the value of the function at 4, you would say f of 4 is, I'm going to plug 4 in here, and I get boop, boop, boop. This is a 3. But if I asked you what is the limit at 4, you would say the limit as x is approaching 4 of this function is, well, on this side it's getting close to a y value of 2, and on this side it's also getting close to a y value of 2, so the limit would be 2. We're going to work through 4 examples. These 4 examples are going to show you all the different ways you can deal with algebraic limits, and then we're going to kind of generalize at the bottom of the page. Okay. So step number 1 is always plug in the limiting value. For example, this says, what is the limit of this rational function as x approaches 1? So I would go and say 2 times 1 squared minus 7 times 1 minus 4 divided by 1 minus 4. And when I simplify that, that gives me, let's see, it's a negative 9 over negative 3, so that's going to give me a 3. If you can get a number to pop out, this means the value and the limit are identical at the point we're talking about. Here's 1. The value and the limit are exactly the same, or the point is the same as where they are approaching. They're both getting close to 3. And you're done. Second example, notice that we have the exact same function, but this time we are approaching 4. Now, when I plug 4 into this guy, I get, let's see, plug a 4 in here, that would be a 32 minus 28 minus 4. On the bottom, I'm getting 4 minus 4. So that would be a 0 divided by a 0. Uh-oh! That's an indeterminate form. Now, if I haven't made it clear before, I'm going to make it clear now. Indeterminate form means we don't know what's going to happen. There might be a limit and there might not. But what we're sure of is that there is something in the denominator that has 4 as a root, right? A root means that when you plug it in, you get 0. So 4 is a root of something in the numerator, and 4 is a root of something in the denominator. So what I'm going to do is I'm going to mess around with this guy right here. I have a feeling that this quadratic can be factored to give us something that has a root of 4. So we could rewrite this as the limit as x approaches 4 of, I'm going to leave the x minus 4 alone on bottom, and on top, I'm going to factor. Now, if you're not great at factoring, I got good news for you. You know one of the factors is x minus 4 because that would have 4 as a root. You just have to figure out what the other one is. In this case, it comes out to be 2x plus 1. All right, well, here's what that means. That means that we can cancel this guy and this guy, and we're just dealing with the limit as x approaches 4 of 2x plus 1. Now that we have found those factors that have 4 as a root, we can go and plug the limiting value, the 4, back in, which means that we would get 2 times 4 plus 1, which is 9. So here's a limit problem that has a solution. And graphically, here's what must have been going on. Here's 4. We must have had something that looks kind of like this, where boop, 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 boop. There's a hole in the graph, right at 9. Let's do another one. So I changed the function just a little bit. I changed the -4 to a 3, which means that, once again, we always start by plugging in the limiting value. In the numerator, we're going to get 4 squared times 2. That would be a 32 minus a 28 plus 3 over 4 minus 4, which would leave us with a 7 in the numerator and a 0 on bottom. Now, you guys know, going way back, you're not allowed to divide by 0. But this one is not an indeterminate form because you have a number on top. If you have a number divided by 0, here's what's going on visually. Here's 4. There is one of those things that rhymes with schmasymptote right here. And the graph must be hugging that asymptote. Now, if the graph is going off to infinity in either direction, then it does not have a limit. So we would say in this case that the limit does not exist. And if you like to do things the quick way, you can write your answers for does not exist problems like this, D and E. That brings us to our last example. Look at this last one here. On this last one, I'm taking the limit of a cubic function divided by a linear function. And if I plug in the 2, let's see, that would give me 8 plus 4 minus 8 divided by 2 minus 2. That's a 0 over 0. Uh-oh. All right, so think about that. What does that 0 over 0 tell us? It tells us that x minus 2 must be a factor of both the numerator and the denominator. So I want to take this numerator right here, and I want to rewrite it as x minus 2 times something. And I know this something is going to be a quadratic. Why, Mr. Klein? Why? Why do I know that's going to be a quadratic? Well, because a cubic has a degree of 3. So if we have a degree of 1 here, we must have a degree of 2 here so that they would add up to the 3. X to the first times x squared is x to the third power. Now, figuring this out, probably not going to be a factoring game for you. I would recommend that instead you do a little bit of synthetic division. So let me remind you how synthetic division works. We're going to divide this guy, which has coefficients of 1, 1, -2, and -8, by this guy right here, which has a root of +2. So you start there, and then you drop the first coefficient. You say 2 times that coefficient is 2. Add them together. You get a 3. So again, you are dropping, multiplying, adding. So let's do that again. 2 times 3 is 6. 6 and -2 gives us a 4. 2 and 4 gives us an 8. Oh boy! Oh boy! Oh boy, I'm feeling good about this, because this and this together, when we add them, gives us a 0, which means that we have a remainder of 0. And we knew that was going to happen because we got 0 over 0 right here, right? So if we hadn't gotten a remainder of 0 right here, we'd be in trouble. What do we get out of this? Well, 1, 3, and 4 are going to be our coefficients up here. So I'm going to call this 1x squared plus 3x plus 4, which means, oh, my paper is a mess here. All of this bananas here can be rewritten this way. The limit as x approaches 2 of x squared plus 3x plus 4. Now, where did I get that from? I said I can cancel this with this, leaving us with this. Now you just do your little pluggy doodles. So 2 squared plus 3 times 2 plus 4 gives us a, let's say that's a 6 and 4, that's 10. That's going to give us a 14 is our answer. So there we go. There's some examples of some problems that you should know how to do. And right here, just to generalize, let's say this. If you want the limit of f of x at x equals c, you plug in x equals c. Isn't that what we did for each example, right? We plugged in first. So if you get a number, then you're done. The limit is the same as the value. And you're happy. If, however, you get a number divided by 0, you're also done. This means that the limit does not exist. And you're done because you're happy. If, however, oh, this got kind of cut off. If you get 0 divided by 0, then simplify. Right? And that means you're factoring. And then plug x equals c in again. All problems will take one of those 3 forms. That's it for your lesson. Go take a look at your homework.